social channels. I'll drop in the chat how you can do so. If you aren't in our Slack channel, would love to have you in Slack and continuing the conversation, maybe continuing today's conversation. And hopefully you found today's session via the Women Who Code events page, but if not, I'll also drop a link to that there. So without further ado, I'll hand it over to Mayatri to introduce our speaker.
Hi, everybody. Good morning or good evening or wherever you're from. This is Maitri Kulkarni, and I am part of Women Who Code from last 1 year or so, and it has helped me a lot to grow personally and professionally. And whoever is not part of Slack, I would suggest you all to join us, and you can contribute or volunteer, and you have many other opportunities to grow technically or professionally. So here we are today with an amazing speaker, Jennifer Bergstrom. She she works for Parsons Corporations as a DevSecOps engineer manager. She has 15 years of experience with IT industry, and she likes keeping herself busy. And apart from that, she few of her hobbies are hiking, and she likes listening to music and spending time with her family. And she is a fun-loving person whom I know. And over to you, Jennifer. Thank you.
Thank you for that introduction. Good morning, good afternoon, and good evening, everybody who's tuned in today. Thanks for being here with us. I'm going to go ahead and share my screen. Oops, I can't share my screen yet.
Let me cancel my screen share real fast. There you go.
Yeah, I should be able to share mine. Thank you. All right. So hopefully everybody can see my title screen now, Chaos Engineering, Injecting Failure to Prevent Failure. So I'm going to jump in. Please feel free, as was indicated earlier, to ask questions if you have them, and at any time, and we'll make sure we get them answered for you. So here's the agenda. I'm not really going to talk to this slide, but I just wanted to have it in here for people so you could see it. So we'll start off with who am I? The ladies already gave me a lovely introduction. Thank you for that. As far as who I am with respect to chaos engineering and why I can talk to this subject, I'm a software engineer who's seen the power of chaos engineering. And I know I say I'm a former software engineer on the slide, but really the software engineer never leaves you even when you move into management. So I'm a software engineer and a technical lead in addition to a few other roles at my company. But I'm a full-time mom. I have two beautiful daughters. Their ages 15 and 13, and they're learning science and STEM technologies and interested in that. And I'm very proud of them. And I am a software engineer for Parsons. In my previous job, I was a software engineer for Lockheed Martin as well. So I do have several years, or 15 plus years of experience with a few different companies. I have a few certifications under my belt, which is partly why I'm participating in the cloud group for Women Who Code. And I'm consistently working to add additional certifications, just because the process of learning to acquire those and to be able to pass the test is a wonderful thing, and I really enjoy doing it. So I had been a software engineer for Lockheed Martin for almost 10 years, and then I stepped out to be a full-time mom for my two girls. When I came back into the workforce in 2015, I didn't know anything about cloud. I had no concept of what that was. I thought they were the big white fluffy things in the sky. I didn't understand microservice design. I had no concept of widely distributed systems. The work that I had done for Lockheed was with monolithic large-scale applications, not with microservices or anything smaller. I didn't worry about system failures. I was a developer. Failure wasn't my job. But now that I'm at Parsons, I design systems and software solutions that operate in AWS and Azure clouds. I include security as a key part of the systems that I create, and the more distributed your systems become, the more important security becomes. And I inject failure into the systems that we create to improve the quality of those systems. So let's talk a little bit about the history of chaos engineering and what it even is and where it came from. So there are several different definitions of chaos engineering. It is a different approach to software quality assurance and testing than what has traditionally been done across industry. Netflix, their definition of chaos engineering is that it is the discipline of experimenting on a software system in production in order to build confidence in the system's capability to withstand turbulent and unexpected conditions. One of the key components of Netflix's definition of chaos engineering is that it is in production. You are doing your testing on your operational system while it is operating and while your users are using it. The chaos engineering community has expanded that definition or simplified it a little bit to say that it's experimentation on a system to uncover its weaknesses. And one of the things that I always have to make a point to mention to folks is that chaos engineering is not the same thing as chaos theory. I'm a math person. I enjoy math. I play with it. And one of the reasons why I went into the degree path that I did when I was at university was because of chaos theory. And chaos theory is a mathematical theory where small perturbations in large complex systems can lead to highly divergent results. And you can see a diagram there on the chart. It's called a bifurcation diagram that kind of illustrates the complexity of chaotic systems. And you can see, looking at the chart, that what looks random often actually isn't, and it can be analyzed and predicted. All that to say, chaos engineering was not actually derived from chaos theory. They have the same first word in their name, but that's as far as it goes for the similarities. Chaos engineering is injecting failure into your system in order to prevent failure in your system. And we'll talk a little bit more about that later. That I know it sounds contradictory. So where did chaos engineering come from? There were a lot of failures in the historic failure testing and the methods that people used and the companies used for years and years and years to test their software and their systems. A lot of times for failure testing, it was conducted as a thought experiment. You would get all of the major players for the system in a room sitting around a table, and they would think about the way that it can fail and try to identify every failure point they could come up with and talk about it and, walk through what the system would do when it failed. It was heavy on hypotheticals, light on actual test execution. You can talk about failure all you want, and you can believe that you have your system designed to fail, but if you're not actually testing it, you don't know for sure if you're going to be successful or not in a failure situation. And when they actually did do testing, it was typically very contrived. You didn't test in prod. That was unheard of. You didn't want to risk taking down your system and damaging it that way and blocking your users from being able to use it. And the test environment often did not resemble what was running in production. It would be smaller, it would have fewer users. It was maybe related, but it was certainly not the same. Oftentimes the testing ended up being something along the lines of, if we kick the system in a very specific way, it can handle that failure. But again, very contrived, very small, and not a practical, realistic test of the system and of failure within the system. And there are a lot of unintended ripple effects of real failures that happen that the simplified historical failure testing simply couldn't test because they weren't looking at it. Their oversimplified testing would miss the knock-on effects of cascading failures. And an example that I list in here is NFS failure or drive failure would lead to a logging failure, which then leads to a database failure, which then ends up taking down the whole system. And you can't really predict all of those follow-on effects easily. So typical failure testing really doesn't mitigate actual failure. It gives you a little bit of a feeling that you might survive it, but that's about it. And it's a growing problem. Historical failure testing already wasn't sufficient. But then our systems continue to get more and more complex, especially as we move into cloud environments. We now design things with microservice design, which means we have multiple moving pieces and parts for our system to build the whole thing. We have geographical distribution, and our contrived environments genuinely cannot simulate reality. If you look at Netflix, their architecture, the diagram that I have here, their actual architecture is worldwide, multi-zone, redundant, multi-cloud, spread across the entire world and running 24/7. It cannot afford to have downtime. You can't test that. You can't replicate that actual architectural environment in a test environment. There's not enough resources available, and you won't have the user load that you have in the real environment. And one of the ways that they tried to address that early on was by simplifying the architecture and testing that simplified architecture. Pretty standard way to do this type of testing. But you can see even the simplified architecture was fairly complex, and yet it didn't come close to matching the real architecture of their system. Increased user base of the software as a service products also leads to user loads that are impossible to simulate and test. As of 2019, Netflix had 61 million users just in the United States. And I imagine that number has probably grown significantly this year with all the events of 2020. So chaos engineering grew from that need to test large-scale, widely distributed systems with millions of users in public cloud. This is an environment and a scale of system that you cannot replicate in a test environment. It is impossible to do so. And the other problem, of course, is that failure does always happen. A lot of times when we're designing systems, we pretend like our system is not going to fail, like it's always going to be there. But it will fail. Hardware fails, software fails, network connectivity fails. There's many different ways that things can fail. And moving into the cloud does not inherently solve the problem of failure. Most cloud services provide 4 nines of reliability across most of their services, which means that the downtime that they expect to have is very minimal. However, there is downtime that is expected. It's not 100% reliability because that's impossible. It's 4 nines of reliability. And while that may only be an hour or two over the course of a year, that still can have a significant impact and cost a company a lot of money. And in addition to that, unexpected outages in the cloud will occur on occasion. And those should be expected and designed to protect against, just like running systems in a data center. So here's some historical failures on major platforms. You can see that I've got AWS and Azure system failures called out. And these were big failures that took a lot of people down and actually completely put some companies out of business because they hadn't designed properly for them. And in addition to the failures of the major platforms that do happen, there are also cyber attacks and distributed denial of service attacks, and those are on the rise and getting bigger. There was one just this year that was a 2.3 terabit per second distributed denial of service attack. It was made against a system running in Azure, and it took them down for several days. So failure is a reality that must be addressed. And how did Netflix want to deal with that with their widely distributed system? Well, they pioneered the concept of chaos engineering. And they started with very simple and small with a chaos monkey in 2010. The chaos monkey essentially was a tool that randomly went into their production environment and disabled servers. And they set it up so that it would be random, so that they didn't know which server was going when, and it could be any server within their system doing any functionality. And it was created in response to Netflix's move from on-premise data centers into the AWS public cloud, because Netflix recognized that the servers in AWS had to be considered more transient than on-prem ones, and they wanted to make sure their design would survive that, both for their customers' sake and for their own business model's sake. And then Chaos Monkey grew. It didn't just stay a single monkey, it became a simian army in 2011, because Netflix pretty quickly realized that testing the loss of a single server is a great start, but it's not sufficient. There's a lot of other failures that can happen. So they started adding elements to their army to address a variety of different failure modes, and some of them are listed here. What if several servers crash at a time? What if an entire data center fails? What if multiple data centers fail? What if a distributed denial of service attack comes in? And what if someone deploys a machine that doesn't adhere to standards? Now that one sounds a little funny, I think, when compared to the other ones. But if a machine is deployed that doesn't adhere to your standards, especially to your security standards, that introduces a vulnerability into your entire system. And that can be a really big problem that needs to be tested for. Netflix scale was so large, as we saw with that earlier diagram of their network, that the only way to test for failure was actually on the production system. And Netflix continues to expand chaos engineering. They open sourced their Chaos Monkey in 2012. And the reason they did that was because they recognized that the best defense against major unexpected failures is to deliberately cause failure often. And by causing that failure frequently, they force their services to be built in a way that's resilient. They created the chaos engineer role in 2014, and that was an engineer whose full-time job was designing chaos experiments and injecting failure into their runtime system. I always thought this would be a really fun job to have. You break things on purpose and they pay you to do it. That's pretty cool, actually. And one of the key components of their chaos engineering role is that they don't work odd hours. They work regular business hours, and they inject their failure into the production system during those regular business hours. Now, why does Netflix do that? They do that because the user load is about what they would expect during regular business hours, because it's regular business hours. So it's a realistic testing. They also do it because if something goes haywire in the experiment, they have their full staff there ready to support things. They're not calling people in at weird hours. They're not having to do funny things to try to fix the system. So it's better for the user, it's better for the system, and it's better for the engineers that are supporting the testing. And Simian Army, as I mentioned, does continue to expand. So here's some of the other actors that they have. My favorite one is Chaos Kong, which simulates the failure of multiple data centers. In AWS, that was initially an entire region that they simulated the failure of, and they've actually expanded it now so it's multi-region as well, that they emulate the failure of. And another one that I like is the Compliance Monkey, which terminates resources that don't follow the environment standards. And again, that's one of the problems and one of the vulnerabilities that engineers can introduce into a system is non-compliance, because it exposes holes in their system. And I see that a question came up: are the chaos engineers responsible for support, or the engineers who develop the system? And the answer is both. The chaos engineers plan the experiments, they coordinate execution of the experiments so that people know when they're going to happen. And then the developers that are writing the system and the system architects and network engineers are all present when that testing is happening. And if something does happen where they need to step in and fix the system, if it's not fixing itself, then the team is all there to support that. And the other question was, is the Simian Army open source? Pieces of it are. Chaos Monkey is, and there is a very active chaos engineering community out there that has created a lot of these members of the Simian Army, or recreated a lot of them. Most of Netflix's specific code is not open source, other than Chaos Monkey. But you can find a lot of resources out there, and I actually do have a link later in the slide that talks to that, or that points to some of those resources. So the key takeaway from all this is that Netflix is continually expanding their failure testing to ensure that no outages repeated. So there's two pieces to their testing. They test for failures they've already seen to make sure that those failures don't break them again. And then they also test for failures that they think might happen to make sure that they're resilient against those failures. But they look for both, and they monitor their system for any unexpected failures that they haven't tested for so that they can add those. And this one is an eye chart. I apologize for that. I know it's pretty close to impossible to read. The key takeaway from this chart is that chaos engineering is not just in use by a few companies. It's not just in use by unicorns. It's a widely accepted method of testing your system for resiliency and for fault tolerance that is used by companies around the world. If you look on this chart, there's a few names that pop out. You can see Fidelity, which is a huge banking company, banking and investment. You can see Facebook. You can see Google, Yahoo, Uber, and of course, Netflix is in there as well. And there's a lot of other ones that are in here. So this is a strategy of testing that is becoming more and more widely accepted across the industry, because there's a lot of power in it and companies are recognizing that. So let's talk about some of the benefits of chaos engineering. Chaos engineering at its root is a tool to learn about your system. Learning from unexpected outages, ones that actually take your system down that you really weren't prepared for, is painful and can be very costly. And that cost is going up and up for companies as they get more widely distributed and more global in their nature. Chaos engineering is like online education. You can learn on your own schedule. You choose when to run the experiments so that you know when it's going to happen. And it allows calculated failure injection and study of the results. So it's a deeply analytic test tool that you can use. It allows you to move from post-mortem failure analysis to pre-mortem failure experiments. You're testing your failures deliberately rather than responding when there's already a fire happening. It's like a fire drill in the office, but one where you actually light a fire. So instead of pretending like there's a fire, you cause one and then make sure your system puts it out without too much damage. Chaos engineering tests, as we mentioned, are often derived from previous failures. And I put the rather pithy little quote in here, an ounce of prevention is worth a pound of cure. That's very true, though. If you've already tested your system for specific failures and you know that it will automatically recover from those, then you save all of your engineers and all of your support staff a lot of stress, and you save your company a lot of money because your system will auto-heal itself when those failures do end up occurring. And in the industry that I work in, a lot of the work that we do actually has real impact on human lives. So we can't afford for that system to fail and not be able to recover itself. Every minute that the system is down, it's putting people at risk. So chaos engineering is a hands-on educational tool. It lets you get in there, it lets you test, it lets you actually play and plan your experiments ahead of time rather than responding to failure. And another key component of chaos engineering that's very valuable is the concept of testing like you fly and flying like you test. Test environments, as we mentioned, are often undersized compared to production. They don't have as many users, they don't have as many servers, they don't have as many network connections, they're not as widely distributed. Differing configurations between test and prod can cause behavioral differences. So some of the testing that you do in your test environment may be invalid in your production environment just because they're so different in the way that they're configured. And different behaviors invalidate that testing when you're off prod. If you're not running it on the same system, you're not really testing the system. Chaos engineering then encourages careful, well-planned testing in the production environment. And this diagram just indicates that, if you plan your testing and run it on a jalopy, you're not actually testing a Tesla, right? They're not the same thing. The test system is not the same as the production system. So testing in that test environment isn't enough to mitigate failures in the production environment because you just can't test all the failures that can occur. It also provides guardrails to a DevOps process. If you use chaos engineering on your system, then you're going to have a strong and resilient system. If you have that strong, resilient system, then you can automatically terminate components that are not compliant with your system rules. And if you can enforce the compliance rules to the rules or the compliance to the rules in prod automatically, then your developers can't effectively push non-compliant or low-quality modifications into prod. So chaos engineering can enforce that compliance in prod. It can scan for forbidden code distributions. It can look for modifications to the environment. It can test your labeling and tagging of resources to make sure that they're all traceable to who created them and why they created them. And it can remove non-compliant resources and notify the owner. Compliance Monkey that Netflix created in their Simeon Army does this to a degree, but there's a lot of open source ones out there that do it even more so. So it allows you to enable strict compliance enforcement without having actual gatekeepers. You don't have people there that are reviewing things and injecting that slowness into the process. It's an automated system. And the developers that put non-compliant components out into the system are notified automatically. It's a clean process that everybody's aware of, so that when you do push something accidentally that's non-compliant, you find that out very quickly and are able to correct it. So some DevOps guardrails: isolating servers with unhealthy CPU and memory load. That's the Doctor Monkey. Janitor Monkey cleans up any unused resources cluttering the environment. That reduces cost, and it also reduces vulnerabilities. You're not paying for resources that are unhealthy or not being used, and you're not leaving them out there for somebody to hack into and try to get access to your system. And it removes those deployed resources that are non-compliant with environment settings. As I mentioned, that's Chaos Monkey. Security Monkey removes resources that have non-compliant security settings. So it again strengthens your system by reducing vulnerabilities that are allowed to remain within the system. So it enables new tools that can enforce compliance. And it does that in a way that's relatively painless to your engineers, because if they do deploy something that's non-compliant, they get notified and they can correct it quickly. So how do we actually implement chaos engineering? We've talked some about the benefits of it and what it can do, but we haven't talked anything about how to actually make this happen. One of the key things with chaos engineering is the experiments are not chaotic. They are well planned, they are well understood, and they are designed carefully to work within your system. So there are questions and knowledge that you have to understand and know for your system before you start injecting chaos. Some of those are, what are your mission critical components? Are they designed and built for fault tolerance? You don't want to test something with chaos engineering if it's not designed to be fully fault tolerant. And there are times when your systems are going to have components that aren't. So what should be able to fail without disabling your system? What are those components that are fault tolerant, that have that redundancy and that resiliency built into them? What components shouldn't? Maybe you have a legacy database in your system that your system is reliant upon, and if you take that down, you're going to kill your whole system. Well, that's probably not something you want to run chaos testing on. What monitoring do you have on your system? Do you have good log tracking? Do you have good performance statistics that you're collecting on your system? If you don't have good visibility into your system, the knowledge that you gain from chaos experiments is going to be limited, because you just don't have the visibility, you don't have the understanding of your system to really know what's going on and any of those cascading failures that can occur from the test, what the impacts of those are. What failures have you seen in your production system? If you've been running this system in prod for a while, you've seen failures. What are they? What have they done? Which ones had the biggest impact on your system? And what requirements in your system could benefit from validation using chaos engineering? There may be some requirements in there for performance or for latency or for failure recovery that are ideal candidates to test with using chaos engineering. And you need to understand those and know what they are so that you can prioritize the testing that you're running. Benefiting from chaos engineering requires a deep knowledge of the system. It isn't something you just go in and start doing. It's something where you prepare by understanding your system very well before you do it. So how do we get started then? First, you analyze. You look at which components have the highest probability of failure. You look at which ones have redundancy and a design that should be able to survive failure. You emulate, which is defining the easiest method to reliably emulate the failure of those components. Oftentimes, this is simply a script, either in Bash or Python or other tools. And you look for techniques that let you automate that failure. And then you test it. You actually test it in a test environment typically first. So again, it's not the same environment as your production environment, but it lets you test the test and make sure that it does what you expect it to do and not more. And then you do game day testing in your test or ops environment. And then if your test environment survives the failure test, then you can test in the operations using the same method. So you're not just tossing something at your operational system that you're not fairly confident your system will survive. And then you automate. If you hadn't already done that, you add automated testing using chaos engineering principles into your build and deploy pipelines. As an example, we have one of our systems that we have a continuous integration and delivery pipeline set up with. And part of the test process that it goes through when we check any code changes in is it actually brings up a production scale stack of that system and then executes a series of chaos tests against that system and logs and monitors the results. And if the system does not pass the chaos testing successfully, then that code change is not pushed out into production. The developer of it is notified and informed of what the failure was, and then they get to go back and work again and make sure that they're building that redundancy back into the system. And then you iterate. You don't stop after you've done this once. It's a continual process. So as you mature your failure testing, as you mature your chaos experiments, you continue to add more, just like Netflix has done. You start small and then you build so that you're building your own army of chaos engineering test tools. It's an iterative process. This is something that you continually work at and it grows with your system. So who should be involved? Well, as you can guess, if you're running tests in production, you shouldn't be doing that in a stovepipe or in a vacuum. You need to make sure that you have cross-organizational approval and that people know what you're doing and are okay with it. So that includes people like the development team, your quality assurance folks, your site reliability engineering team. They're in charge of keeping that system up and running 24/7. You better have them involved with anything you do that's injecting failure. You also have your subject matter experts. These are the ones that just really understand the system and what it's doing and can validate that it's still behaving properly, even with chaos injected in it. You, of course, have your test engineers or your chaos engineers. And then in a system that's heavily used by customers, it's a good idea often to have the customer involved as well and to let them know, hey, we're going to be running this testing just so that there's a heads up for you. If something does go haywire, this is why. It requires stakeholder buy-in. You can't go testing in production without having cross-organizational approvals in place, or you probably won't be working at that company for very long. So let's talk about some tools and best practices for causing that chaos. Now, as we talked about with chaos engineering being an iterative process, you don't have to have any really complex tools. They can be very simple. You can write your own. The stack that I was mentioning that tests chaos within its system as part of the development merging process, we use a chaos gorilla test in that stack that was implemented using a few hundred lines of Python code. And we did that because then we could easily incorporate it into our pipeline and run it and test it and make sure that it worked. You can also look at the open source libraries on GitHub. These are scripts that are written by other chaos engineers and shared to the global community. GitHub Scientist is a framework that allows you to deploy new resources and canary test while protecting end users. And Pumbaa is a chaos monkey for Docker containers, so they're expanding into alternative ways of deploying your systems. And then Gremlin is kind of the granddaddy of the chaos as a service concept. And they're a company that actually tools and provides chaos as a service for you. So you can use their system to readily inject several different types of chaos into your system. Now that Gremlin option is a paid license, so it does cost a little bit more, but as your maturity increases with testing chaos in your system or with conducting chaos experiments, they might be a good option because they've already done a lot of the work to instrument these different types of tests. So chaos engineering can be accomplished with simple tools, or it can be accomplished with a suite of tools, or it can be accomplished with a company that provides it as a service. There's lots of opportunities out there. It doesn't have to be expensive to begin with. It doesn't have to be expensive as it matures. So what are some best practices for chaos engineering? You do want to automate that testing as much as possible. You don't want to be injecting unintended chaos into your chaos experiments by having humans in the loop who might mistype something and cause a bigger problem than you expected. You do want to include a kill switch that allows that test to be stopped immediately if it's going wrong, especially once you've pushed that test out into your prod environment and are testing in the real world. Those rippling cascading failures that happen as a result of a failure that you trigger, they can cause big problems. And we have seen cases before in our system where something passed our test in our test environment, and then we pushed it out into prod and it started to cause really big problems. And if we didn't have a kill switch, a way to stop the test and help the system recover, we would have been in a world of hurt. That's very, very important to have that. Don't test in production if you know that your system's going to fail the test. So I mentioned earlier that you need to know your system and you need to understand which components are built for resiliency and for fault tolerance and which ones are not. If you have a single UPS that's connecting your network to the, to power, don't go unplugging that UPS as part of your chaos engineering. You know that your system's going to fail. If you have dual redundant UPS, then unplugging one is a viable option as a test because the system should survive. Do test during your regular business hours, especially when you're testing in prod. You have more support present, you have faster recovery response if the system does fail in unexpected ways, and you have a regular user load on your system, so it's a realistic test. Do plan and document the testing that will be executed. Again, these are well-planned experiments. They are not fly-by-night. They are not just going in and doing whatever you want. It's well planned, it's well orchestrated testing, and it needs to be documented so that everybody understands what's being done. Start small. Don't try to kill a full data center for your very first chaos engineering test. Start with a chaos monkey or something similar that goes in and removes a server or two, and make sure that you can succeed and survive that type of chaos first before you start adding more and more complex failure modes into the system testing. Test frequently. In a DevOps environment and in an agile environment, we're often pushing code changes multiple times a day, multiple times an hour in some cases. Do the testing at the same time as much as possible. Now, some of the larger tests you may not be able to run with that much frequency because that just injects too much turmoil into your system. But as often as you can test, these tests should be run. We have pipelines that automatically do chaos engineering once a week in our systems just to make sure that we haven't inadvertently checked anything in that causes an unexpected failure. We also do some chaos testing with every single merge to the master branch in our systems. All right, and this is a very good question that Alvita is asking. What if your chaos test triggers an unanticipated failure that does not trigger the kill switch, but still has the potential of bringing your system down? Are you out of luck then? That's a very valid question. One of the reasons why we have both an automatic and a manual kill switch in our system is so that if we do get unanticipated failures that aren't triggering the automatic kill switches, we can go and manually trigger it. But there are situations that perhaps if your test isn't designed quite as effectively as you thought it was, or if it's designed way more effectively than you intended it to be so that it's causing more damage, you could cause actual real failure in your system that you're then going to have to go in and repair. And again, that's partly why you have to have your full team there. That's why you should be testing during regular hours when you have people there. So that if you do have one of those cases that happens, you can recover from it as quickly as possible. And part of the planning and documentation that you have in there is what are the things we think could happen and how do we recover from that manually if the system doesn't recover automatically. So yeah, it's definitely a risk. Anytime you're testing in prod, it's a risk that you're going to inject some failure that will cause bigger problems than what you were prepared to deal with. That was an excellent question. Thank you, Alvita. So again, another best practice is do communicate those tests and their purposes clearly to the entire team. And it ties into the question that Alvita just barely asked. Make sure that everybody understands what's being tested and why it's being tested and what you believe the impacts will be, and make sure that you have support on hand so that if those impacts extend beyond what you expected, you have the right people in the room to be able to fix it and to be able to help the system. So chaos engineering should be well planned, and I had to put a fractal picture in here to tie back to chaos theory just because I really like chaos theory. But one of the things that you see with chaos theory that is similar with chaos engineering is that it is well planned, it's repeated, it's consistent in its behavior, right? This is not something that's fly by night. It is something that you coordinate and plan. And that's it for my slides. So I'll open the floor for any questions that anybody has they may not have asked.
Any final questions? That was awesome. I personally took down some notes. I do a little bit of chaos engineering in the role that I'm in, but not as extensively. So it's phenomenal.
Thank you.
Someone asked, will these slides be shared?
And we can share them. I have been authorized to release these slides by my company.
Okay.
So we can put them out on the Slack channel, or I don't know if there's a preferred means for getting them shared out for people.
We can put them in the Slack channel, and we'll also link them in our GitHub repo. Okay.
So looks like Sunitha asked, would be curious how we got this started at our company. Did it take a lot of work to convince people? Yes, it did. We started it with an independent research and development program that we had running within just our small org within the company. And we built out a small set of chaos tools as part of that IRAD. And then when we were demonstrating the IRAD to other parts of the company, they saw what we were doing and they were curious about it and they asked for more information, and it started to grow organically from there. Now our company is large. There's about 16 to 17,000 employees globally for Parsons, and most of the company still is not doing a significant amount of chaos testing in their systems, but it is growing and it's gradually expanding. How long did it take our company to start from zero to a fully chaos engineered system? Well, as I just said, we're not fully chaos engineered yet. There's a lot of our systems and services that don't do chaos engineering, but it is spreading. For the IRAD that we created, that was a 1-year effort, and we built it in from the very beginning. But again, it's an iterative process too. So our first tests were Chaos Monkey type tests, and we've since expanded it to include Chaos Kong, which emulates the loss of an entire region. And we've added in some latency chaos and some security chaos as well into that system. So it's continuing to grow. I would say that we are not fully chaos engineered even in that IRAD effort yet, because there's always additional tests you can add in. But I do think that we're at a pretty mature state with it. And it took us, again, about a year when we started actively doing it. Is chaos engineering only relevant for systems that handle live traffic? Are there instances of other systems that may benefit from chaos engineering? So I will say chaos engineering was built for web systems that were dealing with users, end users and live traffic. However, I absolutely believe there are other instances that may benefit from chaos engineering. As an example, you may have an infrastructure system that all of your resources rely upon, but that no users directly interact with. You definitely would be value added in adding chaos engineering into that system and testing its resiliency to make sure that your underlying framework doesn't fail as a whole with failure within the system, right? And one of the things that we've been starting to do in our company is we have some isolated environments that are in virtualized private cloud environments or in VMsphere or other systems like that. And we've started injecting chaos engineering into those. Now, those are typically systems that run batch processing, do some machine learning and artificial intelligence on log data and that type of thing. So they're not up 24/7, but we want to make sure that if we, for example, pass in a type of data to them that they aren't expecting, that they don't fail. That's a chaos engineering experiment.
While we wait for any more final questions, I'm going to share some upcoming events that we have, including part 2 of this series. So if you haven't checked out the Women Who Code Cloud events page, feel free to. We have our AWS certification study group going on. Part 2 is all about microservices and the 12-factor application on next Tuesday, again with Jen. Going to be a great session there. So definitely get plugged in with this page, and we're constantly adding events as they come into our backlog. Are there any final questions? Well, with that, thank you so much, Jen. This was awesome. As everyone's mentioned, really great intro and a lot of great insight and tips that you shared. And we are looking forward to our session next Tuesday morning. And thank you all for joining in.
Yeah, thank you all for being here. Please feel free to reach out on the Women Who Code Slack channel if you have any questions about this that you think of after the fact. I am always happy to talk about chaos engineering. It's a really fun thing to be a part of and to work with.
Alrighty, I'm going to go ahead and close our Zoom meeting. Y'all have a fabulous rest of your day.
Thank you.
Bye-bye.